erasure by Felix. Please go ahead. Thank you. Can you hear me on this?
So thank you for the introduction. Thank you for having me here. Thanks to the organizers and congratulations to the organizers actually on this wonderful second iteration of this workshop. I'm very excited. There's been quite a lot of quantum thermodynamics topics already, so this will connect to some of these. And we'll see. So I want to talk about cooling and erasure. So this connects directly to a couple of the things, including the last talk that we've already seen. And I'll speak about this paper here, which came out earlier this year with my wonderful collaborators who are here on the list of authors. And so if we talk about erasure, we can directly start from the beginning and go to Landauer's original paper. You've seen a couple of quotes already this week from the later essay that he published in '91, I think, Information is Physical. I wanted to give a quick excerpt from the original paper here just to get us started, because it has a few of the relevant bits. We're going to do this a lot more general later on, but it has a few of the relevant bits already in it. And so the first part is that what he looks at is an ensemble of bits in thermal equilibrium, and the task of erasure is to reset them to 1 or to 0. I think I'll use 0 later on, but same. And then there's an entropy cost associated to this, which in turn is associated with an energy cost that comes about in the task of erasure. And this is the famous KBT log 2 in this case of resetting, as we'll think about it, a maximally mixed qubit to one or the other of the default states. And what Landauer points out down here already is that this is, of course, a minimum heating effect. And our method of reasoning gives no guarantee that this minimum is in fact achievable. And so I'm not perfectly sure of what he had in mind for this. Did he mean that there are some practical imperfections, but they're not super relevant? Or did he have in mind that there might be some fundamental constraints on achieving this as well? And that's going to be the topic that I want to touch upon here. So just to give credit to the man for already pointing this out in the original paper. So to get started, how do we think about the erasure process? I'm going to give a super simple, intuitive way, hopefully intuitive way of thinking about this. And we can generalize this very easily. So we'll think of an initially degenerate state, as is the case with the original version of Landau erasure. We'll be very happy later on to extend this to qubits with some non-degenerate energy structure, and the entire logic follows straight through. But to see this, let's look at the simple example here first. And then what we can do as the first step is we can raise one of the energy levels to some very large energy, or as large as we want really. And then in the next step, we let that level we let the entire system thermalize with this large energy gap. And you can see that the effect of this is that the ground state population, as now the ground state, goes to close to 1 if the second level is very high. This is super straightforward. We can reset the levels afterwards, and that's now a bit reset, right? That's a paradigmatic way of thinking about this. You'll have probably come across this before. And what's the cost in this? So this is nowhere close to Landauer in this case. This is just a sort of naive, intuitive way of doing this. The cost is basically a half times something very, very large. So we've got nowhere close to Landauer, yeah? But this is a starting point of a primitive of erasing information, yeah? And so to do this a little bit, yes, so we can perfectly erase something so for any error that we're willing to tolerate here on the erasure process, we can find some large energy level that we're going to raise the level to, and with a probability half, that's the energy cost that we get, and as that goes to infinity, good, we can perfectly erase. Here's a way of doing it. But so now to get back to this Landauer energy bound, which is of course the interesting bit. What we can do instead is we can start raising the first level on the right by just a little bit, by an epsilon, say, and then let it thermalize at that point. And we can keep doing this many times, right? And so at some point we reach some higher level. Again, this now has an energy of n times n is the number of iteration, n times epsilon. And we've thermalized at this level. And we've paid a little bit of energy cost at each step, something that looks like this. And what you can convince yourself is that if we take the limit, we have to do this carefully because we're taking two limits at the same time. We take n to infinity and epsilon to 0. This works out nicely. And in this particular case, it gives us back exactly the Landauer limit. Yeah? So if we're happy with taking this limit, this is now a protocol that at the cost of taking infinitely many steps of an infinitesimally small energy change lets us erase this information as before, but now with a finite cost. Yeah? Good. Alternatively, what we can do instead of raising this one step at a time, there's a perfectly analogous way of thinking about this, and you might have come across this before as well, is we take the system and the individual raising operation just corresponds with a swap with a second system, an ancillary system that has a slightly higher energy gap. Yeah? Here as well, we can generalize this to qubits or even infinite dimensional systems, but this suffices for the moment. Yeah? So the energy of the next system is going to be the same as what we had in the previous protocol just now for each step, and we just swap these systems and we have the same energy cost as we had previously. Yeah, and this is the state that we find these systems in. So this is very straightforward, right? This is a way of intuitively thinking about Landauer erasure. The main point that sort of sets up the motivation now for what I want to talk about is that we can realize so each of these unitaries is some swap operation that has a little bit of energy cost attached to it. We can concatenate all of them. That gives us the overall unitary operation, just a concatenation of swaps, and we let the n go to infinity. What we can realize is that, of course, the overall operation is still a unitary operation. Yeah? And in principle, there always exists some Hamiltonian for which we can do, you can see I didn't include a time in here, but for which you can do this in unit time, right? So you apply this really large Hamiltonian now, which has all of these bipartite unitary swaps in it. You apply this in one go, this always exists, right? So now, great, we're still sticking to the Landauer cost, but we're doing it in unit time now. Yeah, so that sounds fantastic, right? So we noticed we can, if we have time diverge, the number of operations diverge, make it very large, make the infinitesimal energy changes very small. That allows us to erase. If we let the energy diverge, it's the first step. We can also have a protocol, and now I'm saying we can actually set both of these to some finite value and still erase it, the Landauer cost. Yeah. Before picking up on this, of course, we can think of this entire procedure now as a cooling procedure, and you'll be happy with this if we have a system that's initially not degenerate. The reset to one or the other side corresponds to cooling to the ground state. The previous speaker has nicely mentioned already that there are two ways that people often think about cooling, either resetting something to a lower temperature or trying to maximize the overlap with the ground state, and for bits or qubits, these coincide. We can think about either of them. But in principle, very, very simply put, we can think of erasure as a cooling to the ground state. Yeah? And we extend this in these ways here by allowing for multiple levels and generally complicated Hamiltonians, as complicated as you like. Yeah? Good. But so now I've said we can do this all in unit time, and now this should send off some warning lamps to anyone who's done thermodynamics before, right? Because if we now think of this erasure process as a cooling process, what I'm saying is we can in unit time cool something to zero. That seems to be directly a strong conflict with the third law of thermodynamics, yeah? Which says that you cannot cool to a zero temperature with finite resources. Yeah, that's an unattainability principle. This seems to be a problem. Yeah, so where's the catch with this? And you can probably spot it already. This is going to be the main point that we want to resolve then, yeah? And the catch is going to be that we found this Hamiltonian, which allows us to do this entire cooling procedure at the optimal energy, at the Landauer energy cost. But this thing is in general, of course, a very maybe non-physical Hamiltonian, in the sense that this is going to be all of these swaps brought together into a single operation. This is going to be something very non-local, intuitively speaking, yeah? Or maybe we'll be a little bit more careful and we'll call it complex, because we could try to replace the non-locality, the many bits, by actually using larger dimensional systems and taking the dimension of one system to infinity and interacting with many levels. But in either case, this thing is something that is going to be very complex, and the idea is that this is not going to be something physical in the limit of this working out as a unit time operation. I hope this doesn't clash with anyone else's intuition. This should be the very expected thing to get at this point. But it makes the point that the normal thinking about the Landauer erasure, there's a third type of resource to it, which we can intuitively now identify, and we want to get a little bit more precise on that. Yeah, the third resource is something that we might as well call a complexity. There's going to be a little bit more nuance to that. Good. So to add a little bit more nuance to this, let's do this more carefully. And we can do this in one of two ways, which we call the coherent and the incoherent control paradigm. You might also call the second one autonomous, and the first one that's a sort of full control type paradigm. So what do we have? We have a system and something that in the literature is usually called a machine. That's the SLA. Yeah. So there's some large external system which is not necessarily a heat bath as such, but something that we can very fine-grainedly interact with potentially. And in the first coherent picture, what we're allowed to do is to do any unitary on this joint system. So everything that we've used in the simple language until now is motivated within this paradigm. Yeah. And then what we can do is we can do some unitary, do some control, and we have available an environment at a fixed temperature, which we can use to thermalize things along the way. Yeah? Very fine-grained control. I get to the incoherent picture at the end, but I just mentioned already how that works in contrast. So in this case, we have the system, and we allow ourselves a hot and a cold bath. But what we want to do is we don't want to actually control them very precisely. We want to be able to switch on an energy conserving unitary. At the beginning, let the thing run autonomously and turn it off again, and give ourselves access to thermality for the two heat baths. Yeah. So this is an alternative picture which is more closely related to the thermal operations way of thinking, but including two heat baths, of course. Otherwise, nothing is going to happen. I'll focus on the first one now. So if we want to look at this a little bit more precisely, we can look at the literature and what's fairly well known, which is the equality version of the Landauer erasure. And it works like this. So you take your system state, this is the system that you're trying to cool, it has some finite dimension, let's say, and you append this machine state. This is going to be something in general that's very large and potentially complex, such as the many bits in the simple example from the beginning that we want to swap with. This entire thing is evolved unitarily according to some precise control mechanism. And hopefully what comes out is now a cool state at the end. Yeah? And so the equality version of the Landauer erasure of the cost is that the energy that is expended on the side of the machine so this is going to be dissipated as heat afterwards, is equal to the entropy change of the system. So this is the initial entropy minus the final entropy. The remaining mutual information between the system and the machine, and then the relative entropy between the input state of the machine, the original state, the start uncorrelated, and the output state. Yeah, and if we, for instance, if we want to cool to the ground state, this thing is going to vanish just by virtue of directly you can see this because we want the pure state to come out of here. So in general, it's going to be this thing, which is going to be tricky for us to reduce, right? So you can see that both of these terms are positive. If we drop them, we get this inequality, which is the more general version of the Landauer erasure cost. Yeah, so we'll call this the Landauer limit or the Landauer cost. And this is the part that we're trying to take to zero over here. Yeah, and so you can see from here directly, which some of my collaborators refer to this as pure states being a convenient fiction. And you can see this from here actually, that if you start in a thermal state for your machine and you want to go to a pure state, that if you start in a thermal state of the machine and in a non-pure state of the system, you somehow have to reduce the rank of the system, and you can only do this if you initially don't have a full rank machine, which has this relative entropy diverge. Yeah. This goes to the limit of dividing by 0 for the output state of the machine. Yeah? I hope that makes sense. Good. So this is gonna be what we start on. This is a super easy to derive equality. Actually, you only have to look at the change in mutual information and give the expression for the relative entropy with respect to the initial thermal state that goes in here, and all of the rest pops out in 2 lines basically. So now the question is how far can we cool with this in principle? Yeah. And so one thing that we can see directly is that this is all going to be unitary. So we have some spectrum that comes out of the initial system, which is not pure because we want to cool it, and out of the machine, which for thermodynamic consistency is also full rank because it's in a thermal state. So the lowest eigenvalue that we can hope to put onto the system at the end is lower bounded by whatever lowest eigenvalue it started in, and then the lowest thermal eigenvalue that the machine starts in, and this depends on the maximum energy gap that's available to the machine. Yeah, this is it's fairly straightforward. This just comes from unitarity, yeah, of having to preserve the spectrum. So this directly gives us a bound, and what we can see from this directly is that if we want to perfectly cool to the ground state, a machine has to have available a divergingly large energy gap. I'm setting here the ground state energy of the machine to 0 just to keep it a little bit easier. So the largest gap has to diverge. This is not the energy cost, but the population that comes from that. For that to go to 0, this has to diverge. Yeah? And then secondly, I apologize for these characters being a little bit funny there. What we can see, so we're not just interested in cooling to perfect 0, right? We want to cool to some epsilon or below level of ground state population or temperature. We're not just interested in the perfect cooling. And so what we can see is that if we want to cool from one thermal state to another on the side of the system, in general, what we need what's required of the level of the machine is that is infinite dimension on the machine. And this is again to do with the rank and being able to make the relative entropy match, as we've seen. Good. So what we have, to sum this up until here, the structural requirements for perfect cooling, we have to have an infinite energy gap on the machine available and infinitely many levels to get to the Landauer cost. That's a structural requirement before we even do anything. Now the interesting bit is going to be the control complexity, what we actually do on this compressed unitary is the many swaps brought together to take the system to the cool state. And that's going to require some form of complexity. I'll just give two examples of this, which we propose. So one is the effective dimension of the unitary. We can try and decompose the unitary into a part on which it acts trivially and non-trivially. And what we can see is that this effective dimension must diverge in order to cool to the ground state. And as a second, more nuanced version, we can see what also must diverge is the variety of the energy gap. So we make a set of all the energy gaps that are available to the machine. And what turns out is they need to be in this interval of the energy gap of the system up to infinity, or very large, let's say. They need to be continuously and densely covering that range. If there's ever a finite gap in the energy structure of the machine, that will cause a finite size cost to the Landau erasure, which will be an additional energetic cost. So that's the second form of control complexity. So we can see with infinite energy and infinite time and infinite complexity, with all of these, either of them diverging, we can cool perfectly. I'll skip this part, and I'll just mention before wrapping up the incoherent version, which we do, where we do the same thing again, but we get a different bound, and this is very interesting. So what we want to do is we want to increase the free energy of the system, reduce the entropy of it. And the bound that appears once we have this comes directly from the energy conservation requirement, is a Carnot efficiency that multiplies onto the energy requirement. So this is something that's going to be between 0 and 1. And we only have the Landauer limit in the case where either the hot temperature goes to infinity or the cold temperature, the ambient temperature, goes to 0. In all other cases, there's an additional gap for this autonomous picture of how costly it is to cool. So with that, let me summarize. We have two pictures, the coherent cooling picture and the incoherent cooling picture. There's a resource that we hadn't previously accounted or maybe noticed that we could use instead of time or energy for perfect cooling, which is complexity. We have a couple of candidates for it, of how to look at the complexity. And we can also do the same thing incoherently, where we can't cool at the Landauer bound. But there's a new bound called the Carnot Landauer bound, where if we allow time or complexity to diverge, we can reach that. And diverging energy, the amount of energy drawn from the hot bath going to infinity, doesn't help us in this case. And so to give a mini outlook, what would of course now be interesting is I've looked at all these resources that diverge, is how do they trade off in finite size, right? So how much energy does it cost if we're trading off between a bit of complexity, which is now finite, and a bit of time, which is not finite? One of them needs to be infinite if we want to be perfectly at the Landauer cost, but how much energy does it cost to get close to the Landauer bound? Good. Thank you.
Now let's move to discussion time. If any questions or comments?
That's a great talk, Felix. Just a quick query. So, as you mentioned, there are some very interesting relations between complexity and in terms of erasure. I'm just curious. So, would one sensible notion of complexity here be sort of just simply the cost if we were to try to implement those complex Hamiltonians using only two local Hamiltonians? Because if you look at, say, the theory of computational complexity, there's this notion that if you have unbounded number of interactions, then something is not a reasonable model of computation, that any reasonable model of computation, the number of interacting components at any particular time must be bounded. And that gives us a notion of computational complexity. So it seems to me that the computational complexity, if you require it to do a single Hamiltonian there, will simply scale exponentially with n, which is why we kind of need to sort of we need to think about So if we wanted to only impact local Hamiltonians, the time will scale towards infinity as well.
Thanks, Miller. So that's a very good question, and the answer is yes. If we're looking at qubits or a finite dimensional system with a fixed finite dimension, we can think of it like this. Yeah. So we can think of each of these is going to be a swap, so we can think of the number of C0s really in a very computational sense. We're not happy with that generally being the notion of complexity, because we could allow ourselves to trade off some non-locality. I've not mentioned what we've done in the paper as well as to look at harmonic oscillators and interaction by, for instance, using Gaussian operations, more non-Gaussian operations more generally. And so this is not a sort of broad enough definition of or sense of complexity.
Dimensional sentence.
Yeah. So if this is your context, that you're doing this entire thing on a qubit chip of some sort, or that's exactly the interest. Yeah.
I guess then it's quite related to the previous talks on the complexity entropy in that sense when you look at there. But you're looking at the more broad picture.
Yeah, so Philippe was presenting this uncomplexity resource. I think that's what you mean. And I'd be curious to see how this relates, right? Because that's a state transformation. Here we're more interested in a sort of entropic desideration to cool to zero.
And here more looks, you're right, this is more of an operation rather than a state. You're right. Thanks.
I have a principal and easy question, which is an infinite dimensional band is by no means unattainable, right? We have many thought bases kicking around. So that in itself is not by a barrier to anything.
Thanks. Yeah, that's a very good question, and something that maybe I should stress here. So there are two forms of complexity that we think of, right? One is sort of structural, and one is on the level of control. So the infinite dimensionality of this is sort of the boring prerequisite for anything on this side to actually work. So that part is perfectly physical. In a way, we're not worried about this. So thanks for pointing this out. That's important, right? We're not worried about the infinite dimensionality of these things. What we need to figure out is how do we in practice actually access these dimensions.
Yeah, the way you said it in your talk was like, that's the problem. Like,
No. Thanks for pointing that out. Yeah.
Now, ready to speak again.